In this video, we apply some of the techniques that we studied earlier this semester to another function involving an exponential. So we've got f of x equals x squared times e to the negative x. And we might want to find the relative extrema, points of inflection, and then use that information to graph the curve. We notice that as x goes to infinity, this expression goes to infinity, and this expression approaches zero. So we have an infinity times zero indeterminate form. But if we want to, we can get rid of that infinity times zero indeterminate form. By rewriting this as a quotient. So the limit as x goes to infinity of this is actually x squared divided by that exponential function. And now we've got an infinity over infinity indeterminate form, and we can apply L'Hopital's rule. So we'll take the derivative of the numerator and the derivative of the denominator. We'll take the limit of that instead. And as x goes to infinity, it turns out that that's still an infinity over infinity indeterminate form. So we will compute the derivative, or compute the derivative of the numerator and denominator again. And then we have 2 divided by a very large number, because this is going to infinity, is a very small number. So the limit is 0. So that tells us the function, or the graph of the function, has a horizontal asymptote. Sometimes I'm not sure if I should be saying the graph of the function or the function itself. Has a horizontal asymptote, y equals 0, and that it approaches as x goes to positive infinity. And as x goes to negative infinity, I'm pretty sure all those calculations would stay the same, right? We'd have infinity times 0. I'd still have an infinity over, well, actually, if x goes to negative infinity, we have a very large number, a very large negative number squared is a large number, and then I'd have a negative times a negative, which would make that a very large positive number for my exponential. So as x goes to negative infinity, since we have e to a large positive power at that point, this is just an infinity times infinity, so we get infinity. So we know that the end behavior on the left is this, it goes to infinity, and on the right, the function approaches 0. The question is, what happens in between? Well, in order to figure out what happens in between, we can find the critical points of f, see if we've got any relative extrema. So we'll compute the derivative. And because we've got a product, we'll use the product rule. This is our first function, and this one is our second. So according to the product rule, we'll have the derivative of the first times the second undifferentiated, plus the derivative of the second. The derivative of e to some power is e to that power times the derivative of the inside. The derivative of a negative x is -1 by the chain rule. This is the derivative of the second, and then we want to multiply by that first undifferentiated. Now we see we've got an e to the negative x term in common here and here. So we'll factor that out. And we say e to the negative x times 2x gives us this first expression. And e to the negative x times a negative x squared gives us the second expression. So f prime is equal to this. And we're interested in the critical points of f. So we want to know when this equals 0 or when this is undefined. Now, e to the negative x can be written as an e to the x in the denominator. But e to the x is always positive. Remember, it just looks like this. So this is actually well-defined for all real numbers. So the only critical points that we're interested in are those that cause this function to be 0. So we'll set this equal to 0, which means that our polynomial is 0. If I factor out the x, I get x times 2 is at 2x, and x times negative x is that x negative x squared. And so we've got 2 critical points, x equals 0, and then this corresponds to x equals 2. So the only way we have product of 0 is if the first factor is 0 or the second factor is 0, and those are the x values that cause those factors to be 0. And so these are our critical values. And we can look at the sign of f prime at those, or on the left and right of those 2 critical values to determine whether our graph is increasing or decreasing on those intervals. And then we can look at whether or not f prime changes signs at those x values determine whether those points or those x values correspond to relative minima or relative maxima. Let's do that. Actually recycling a lot of my scratch paper here. Sorry, that's very different. So we have f prime equals 0 when x equals 0 or 2. And f prime is the product of e to the negative x and 2 minus x. So we'll create a sign chart for f prime. We list the critical values 0 and 2 on the number line in the correct order. And we look at the sign of each of these factors because f prime is the product of this and this and this. But e to the negative x is always positive no matter what x is. Now when x is positive, of course x is positive. When x is negative, x is negative. When x is greater than 2, 2 minus a number that's greater than 2 is going to be negative. And then 2 minus a number between 0 and 2 is positive. You can just pick a test value, x equals 1, 2 minus 1 is 1, which is positive. And then here, if we're subtracting a negative, that's the same as adding. So we're going to have 2 plus a number, positive number, which is positive. So f prime is a positive times a positive, which is negative here. Then it's a positive times a positive times a positive, which is positive. And then a positive times a negative, which is negative. And we know that the derivative is 0 at this point and this point. The function goes from decreasing, having a 0 slope, to increasing at 0. So we're going to have a relative minimum there. And then the function goes from increasing to having a 0 slope to decreasing. So we'll have a relative max there by the first derivative test. So we'll say f of 0, which is, well, remember our function f of x was x squared times e to the negative x, is 0 squared times e to the opposite of 0. So we have 0 times e to the 0, which is 1. So that's 0, corresponds to a relative min, or is a relative minimum. And it occurs at x equals 0. And then f of 2, which is 2 squared times e to the negative 2, or 4 divided by e squared, is a relative max. And that is all by the first derivative test. Okay, well, now I know where I have relative extrema. I can graph the function. And I might also be interested in any points of inflection. So to find points of inflection, we'll compute the second derivative. That's the derivative of the first derivative. And rather than using that factored form of the first derivative, I'll use that polynomial times e to the negative x. And we'll use the product rule again. That way I have only 2 factors for f prime rather than 3. So say, okay, f double prime is the derivative of this product. So we get, for the derivative, the second derivative, the derivative of the first. The derivative of 2x is 2. The derivative of negative x squared is negative 2x by the power rule. For the derivative of the first times the second undifferentiated, plus the derivative of the second. The derivative of e to some power is e to that power, times the derivative of the inside for the chain rule. And the inside function is negative x. Derivative of negative x is negative 1. So that's derivative of the second, and then we multiply by the first. Oops. Sorry, that should be 2x minus x squared. And then we look at this expression and this expression and see that they both have that exponential in common. That happens every time we use the product rule involving an exponential. We're going to have the exponential from the function undifferentiated. We're also going to have the exponential from when we differentiate the function. So we'll be able to factor out the exponential. And then we'll say, okay, well, what's left? After I factor out an e to the negative x from this, what am I left with? Just the 2 minus 2x, right? And then here, you say after I factor out that e to the negative x, what am I left with? It's negative 1 times this expression. I'll distribute the negative. Negative 1 times 2x is negative 2x. Negative 1 times negative x squared is positive x squared. And so what we have is this exponential times x squared minus 4x plus 2. And you might say, is there an x value where that is equal to 0? Well, we could use a quadratic formula if we want to find the x values where this is equal to 0. Or you can complete the square and set it equal to 0. Or you could set it equal to 0 and complete the square to find the x values where that's equal to 0. Either way works. Whichever you prefer is fine. Okay, so let's do that. All right, so I've got f double prime is equal to this polynomial times e to the negative x. We're setting that equal to 0 and solving for x to find potential points of inflection. All right, so you say, okay, if this exponential is always positive, then the polynomial must be equal to 0. And you have some options. What would you prefer? Quadratic formula, or should we complete the square? Well, that's what I was saying in class typically. Since you're not here, since you're watching this at home later, I think I'll just complete the square. To complete the square, what I do is I move the constant term to the other side, make sure my x squared has a coefficient of 1. If there was a number in front of this, like a 3, I would divide everything by 3. But I've already got a coefficient of 1, so I'm fine. Then in order to complete the square, I identify the coefficient of x. I'll call that b. Take half of that, that's -2, and square it. -2 times -2 is 4. That 4 is what we add to complete that square, and that's fine as long as we add a 4 to the other side as well. Then on the left-hand side, we've got something that factors, and on the right-hand side, we just have a number. So we actually add on the right-hand side, we just get a 2, and this factors to x minus 2 squared. If you're wondering how to factor that, you know it's going to be something squared. So you say, well, what do I square to get the 4? It's the 2. It needs to be negative because that middle term is negative. So you have a -2 there, and then x times x gives you x squared. So the first terms in both of those parentheses need to be x's. So you have x minus 2 squared equals 2. So if I want to get x by itself, I take the square root of both sides. Don't forget the plus or minus on the right. So I have x minus 2 equals plus or minus square root of 2. And then if I want to solve for x, I add 2 to both sides. So I've got 2 plus the square root of 2 and 2 minus the square root of 2 as potential points of inflection. Now, in order to determine whether our graph is concave upward or concave downward, we list those x values on a number line. Smaller one first, so we'll have x or 2 minus the square root of 2 and 2 plus the square root of 2. And then we will look at the sign of this factor and this factor. Well, the exponential is always positive. That actually doesn't change anything. So what we're really interested in is this polynomial. And say, okay, well, what does that look like? Well, I know it's kind of hard to see because I solved this equation by completing the square. That's not the same as rewriting the function by completing the square. So let me do that now. We said f of x equals, or not f of x, I'll just call it y equals x squared minus 4x plus 2. We said in order to complete the square, we'll add a 4. That's fine as long as we subtract 4, right? We don't want to change the value of anything. We have y equals x minus 2 squared minus 2. So this is a parabola with a vertex at x equals -2, or x equals +2, y equals -2. And since the coefficient of x squared is 1 there, or the coefficient of this x minus h, or x minus x naught squared is a 1, it's just a parabola facing up. Since the 1 is positive, it faces up. And since it's just a 1 and not a 2 or a 5 or something like that, it's just sort of looks like that typical parabola y equals x squared. It's just been moved. We just moved it to the right 2 units and down 2 units. But it has the exact same shape as y equals x squared. If I graphed y equals x squared and then I graphed this function, then I set them on top of each other without the axes, you wouldn't be able to tell the difference. They have exactly the same shape. So you say, okay, with that in mind, with this picture, what is the sign of this factor x squared minus 4x plus 2 on these 3 intervals? Well, the 3 intervals are determined by those zeros. This function was 0 at this x value and this x value. This x value is 2 minus the square root of 2, and this x value is 2 plus the square root of 2. And we found those by completing the square as well. So you say, okay, how can I determine the sign of this function on these intervals? Well, I just look at the graph. And I can see, trying to find my highlighter, that my function is positive here and here. the y values on that graph are positive because the graph lies above the x-axis. So this function is positive on this interval and this interval, and the function is negative in between. So it's negative here. So f double prime is a positive times a positive, which makes it positive there. A positive times a negative, which is negative, and then a positive times a positive on the last interval, which makes it positive. Now, when we interpret this, this is not increasing, decreasing, increasing. This is f double prime. So this tells us the graph is concave upward here, concave downward here, and concave upward here. And since f double prime changes signs from positive to negative at this x value and negative to positive at this x value, and this x value and this x value are in the domain of the original function. These are the x coordinates of points of inflection. So we need to substitute these x values into the original function to find the corresponding y value at those points. And then that ordered pair xy is a point of inflection. And that's where our graph will change from concave upward to concave downward. And then this xy pair, or the xy pair corresponding to this x value, the graph will change from concave downward to concave upward. So we'll have f of x equals x squared times e to the negative x. So I've got 2 plus or minus the square root of 2 squared. E to the 2 plus or minus the square root of 2. And what we get is 4 plus or minus 2 times 2 times, or 2 times this times this. So it's going to give us 4 square roots of 2 plus 2 times e to this power. So we get negative 2 minus plus square root of 2. And this can simplify to 6 plus or minus 4 square roots of 2 times e to the negative 2 minus plus square root of 2. If you're saying, oh, well, what does that mean? We'll just read the top sign first and then read the bottom sign second to get f evaluated at 2 plus the square root of 2 and f evaluated at 2 minus the square root of 2. So my y values are f of 2 plus the square root of 2 is 6 plus root 4 times the square root of 2 times e to the negative 2 minus square roots of 2. If you want, you can factor out a negative there. And then if you evaluate at 2 minus root 2, you end up with 6 minus 4 root 2 times e to the negative 2 plus root 2. Okay, so those are our values. Let's look at those points on the graph. And then let's verify that our graph is concave upward, concave downward, and concave upward on the appropriate intervals, negative infinity to 2 minus root 2, 2 minus root 2 to 2 plus root 2 is it's concave downward, and then 2 plus root 2 to infinity, it's concave upward again. All right. I want to make sure the audio is working. Is it working? Okay, it is. Just making sure. I wanted to see it. So first we computed f prime. We used the product rule. We said derivative of the first times the second plus the derivative of the second, which introduces a factor of -1 times the first times that exponential. And that's what the first derivative looks like. So we see the first derivative is 0 at 0, and it's also 0 at 2. So by the first derivative test, x equals 0 and x equals 2 are critical points of the function. Now, since the first derivative changes from negative to 0 to positive at x equals 0, that means the original function goes from decreasing to having a 0 slope to increasing. So the original function should have a relative minimum there. And that's actually what we see. And then at x equals 2, the function goes, or the first derivative goes from decreasing, or excuse me, the first derivative goes from positive to 0 to negative. And when the first derivative is positive, the original function is increasing. So we see the tail function is increasing. And when the first derivative is negative, that means the original function is decreasing. So the original function goes from increasing, having a 0 slope, to decreasing. So at 2, the original function has a relative maximum. So you say, okay, that is consistent. The graph of the derivative which is this purple graph, and the graph of the original function, which is the teal curve. Both of those sort of tell the same story. They're consistent with each other. Now, one other thing I want you to notice is that the relative extrema of the first derivative corresponds to the, what's it called, points of inflection of the original curve. And the points of inflection of the original curve correspond to zeros of the second derivative. So the first derivative has an extremum, like right there. It looks like a relative maximum there. So the first derivative goes from increasing to decreasing at this 0.5879. So since the first derivative is increasing, before we get to that point, the original graph should be concave upward there. And then since the function is decreasing after that point, the original graph should be concave downward. And the corresponding XY pair on the original graph should be a point of inflection. And if we look at the original graph, that's what we see. It's concave upward over here. It's concave downward over here. Say, okay, that's cool. Are there any other extrema of this first derivative? Well, yeah, it's kind of hard to see, but there's one. It goes from decreasing to having a zero slope to increasing. So this x equals 3.41 seems to be a point of inflection as well, or seems to be the x coordinate of a point of inflection. So we look at the corresponding point on the original graph. Does the graph seem to go from concave downward to concave upward? I think it does. Because on this interval, the original function, or excuse me, f prime is decreasing. When f prime is decreasing, that means the second derivative is negative. And if the second derivative is negative, that means the original function is concave down. So this is concave down. And then here, the derivative is increasing. The derivative is increasing. Then the second derivative should be positive, and that means the original function should be concave upward. Okay. All this would be easier to see if we just took the derivative or took the second derivative. So we want to take the derivative of this. Now, in here I added some pieces. I said, let's call G1, G2, and G3 sort of the function on 3 intervals. So G1 is this first interval. When we go from negative infinity to 0, you see the function's increasing there. On the interval from 0 to 2, I've graphed it in green. The function is decreasing, or excuse me, decreasing on the first interval, increasing on the next one, and then decreasing on the last one. So we can see that decreasing, increasing, decreasing if we graph the function on those 3 intervals. And then I claimed that at 2 minus root 2 and 2 plus root 2, we had points of inflection. I believe that's the exact value of this x coordinate and the corresponding, or this x coordinate. And if we zoom in, we see that that's our relative extremum. That's our maximum of the first derivative and the minimum of the first derivative, or a relative max of the first derivative and a relative min of the first derivative that correspond to those points of inflection. Now, it's easiest to see that if we look at the derivative with respect to x of the first derivative. And that's the definition of the second derivative, right? So let's do that. By the product rule, we get the derivative of the first, which is 2 minus x squared, times the second, plus the derivative of the second, which is -1, times the exponential, times the first. And that -1 came from the derivative of the inside. And we factor out the exponential, and that's what we have. Now, if I distribute that negative through these parentheses, oops, this should be an 2x, sorry. Derivative of the first is 2 minus 2x. And then we have times the second, which is the exponential. We factor that out, plus the derivative of the second, which is a -1 times the exponential times the first. So that's a negative and then the first right there. Now, if we distribute the negative in the parentheses, we have a -2x plus x squared. And then if we simplify that, we've got x squared minus 4x plus 2, or you can write it in this order. That's fine as well. Now, you can't Desmos doesn't like it when you have this equals this, which equals this. So I'll just write equals that. So we can graph it. And now let's look at it. Okay, look, f double prime is 0 at this value and this value. I claim that those are 2 root 2 and or 2 plus the square root of 2 and 2 minus the square root of 2. 2 plus the square root of 2 is over there. It's that point. Just plotted the point and labeled it. And then 2 plus or 2 minus the square root of 2 is there. That's that point. There's way too many points on here. I think I want to delete some of them, or not delete them, but maybe just not label them. The graph is getting really busy. And maybe to simplify the graph as well, let's get rid of that first derivative graph for a second. Maybe not. Maybe I just want to stop labeling all of these. All right, so now let's look at this graph. We see that the green function is 0 at that x value, which corresponds to that 2 minus root 2 here, this 0.58579. That one is the 2 minus root 2, and this 3.41421 is 2 plus root 2. We see the second derivative is positive to the left of that first 0 and negative to the right. And then for the second 0, it's negative to the left of the 0 and then positive to the right. The claim is the original graph is concave upward over here, and then concave downward in between these two guys, in between the two zeros of our second derivative, and then concave upward again. And I think that's what we see. We see concave upward, concave downward, concave upward. And then we also see that the zeros of the green function, that's our second derivative, corresponds to the relative extrema of the purple function, which is our first derivative. The first derivative has a max when the green function is 0. So the green function goes from positive to 0 to negative, when the purple function goes from increasing to having a 0 slope to decreasing. And that's what we would expect. And the second derivative goes from negative to 0 to positive, when the first derivative goes from decreasing to having a 0 slope to increasing. So that's what we would expect as well. So these 2 points on the original graph are points of inflection. Now, if I stop graphing those zeros, or I stop labeling those zeros, then maybe let's get rid of the graph of the second derivative and the original, or in the first derivative now. We see the original function. And we see all those interesting points on the original function as well. Now I graphed the original function a number of times as well on the various intervals to emphasize where it was in concave upward and concave downward. When I highlight this g sub 5, we see that the original function, which is the teal part here, is concave upward until we get to this 2 minus root 2. And then from 2 minus root 2 to 2 plus root 2, the graph is concave downward. And then from 2 plus root 2 to infinity, the graph is concave upward. And that's it. And then I also verified that the second derivative at 0 and 2 had the appropriate signs. So the second derivative at 0 is 2, which is positive. That means the graph is concave upward there. Since the graph is concave upward and the first derivative is 0, we must have a relative min. And then the second derivative at 2 was a negative number. So that means the graph is concave downward. Since the graph was concave downward and the first derivative was 0 at that x value, we have a relative max. The second derivative test gives us the same conclusions that the first derivative test gave us. So that's it. I have that sort of floating purple point here, the maximum of G prime. Get rid of that. So that is the original function.